We have this geometric idea that the span of some vectors represents kind of geometrically stretching those vectors out and kind of letting them reach out in all combinations that they can reach, which gives you some sort of shape, often a plane or maybe a 3-space sitting in 4-space or something like that, which is nice, I guess, but it's a little hard to see how that idea would come up in applications. Not that you need an application to make math interesting, but some people like having applications. So I thought we could look at one from chemistry. So suppose we have a couple reactions. Here's the net reaction for respiration and for fermentation. So respiration is how your body, or every eukaryote's body turns sugar, combines sugar and oxygen and turns it into carbon dioxide, some water, and then also some energy, which is really why we do it, to get the energy from the sugar. Fermentation is an alternative process for getting energy from sugar that doesn't depend on using oxygen, but it produces less energy, which is why our bodies would rather use respiration instead of fermentation. Also, the byproducts of fermentation can be bad for you. All right, so how to see how span applies to this situation, we would have to first think of a good way to encode some information about these reactions as vectors. And one way of thinking about a reaction is it gives you a move that you could make. If you had some number of sugar molecules and some number of oxygen molecules, you could use this reaction once to decrease the number of sugar molecules by 1, the number of oxygen molecules by 6, and that then increase the number of carbon dioxide molecules by 6 and the number of water molecules by 6. So a reaction kind of gives you a move that you can make. Right? If you start with some reservoir of reactants, you can sort of change what you have by this move that this reaction lets you make. So what we'll do is we'll describe the move that you can make using a vector. So the first vector will be the change in sugar molecules. This is actually a particular sugar. I think it's glucose. The second entry will be the change in oxygen molecules. The third will be the change in the number of CO2 molecules, and then the change in water molecules. And then the last molecule in this whole setup is this C2H5OH, which is an alcohol, I think. So C2, I will admit to not knowing much chemistry and even less organic chemistry. So, all right, so we have this vector that is going to describe the move that a reaction makes. So this first reaction, the respiration reaction, let's see, if we did this reaction, it would decrease the number of glucose molecules by 1, decrease the number of oxygen molecules by 6, increase the number of carbon dioxide by 6, increase water by 6, and leave the number of alcohol molecules unchanged. Okay, so this vector represents sort of doing this reaction once, kind of. Fermentation will have its own vector. So fermentation, it uses 1 sugar, so it decreases the number of sugars by 1, doesn't use any oxygen. It produces 2 carbon dioxide, no water, and 2, again, I think that this is an alcohol. All right, so each reaction kind of gives you a move that you can make. So what is the span? Well, remember that's the wonkiest S I've ever written. What span does is span lets you combine these 2 moves in any linear combination. So you could do any number of respirations and any number of fermentations. So you could use up your reservoir of molecules in any combination. So what this span is telling you is all possible moves that you could make, all possible ways you could change the number of molecules that you started with. Right, so that's what this span is telling us. And clearly, since these 2 vectors are not parallel to each other, just as vectors sitting in R5, since they aren't parallel to each other, this collection of all possible moves is going to be some kind of plane sitting in move space, I guess, the space of all possible changes you could make. So of course, since this plane isn't filling out all of R5, it doesn't fill up R5. One thing that this tells us is that you can't get to an arbitrary combination of molecules, because the collection of moves doesn't fill up the collection of all, the collection of all actual moves doesn't fill up the collection of all possible moves. What we might do is contrast this example to the example with, say, respiration and photosynthesis. On net, photosynthesis actually just looks like respiration in reverse. So respiration, let's see, if we had glucose, O2, CO2, and then water. This time we don't need alcohol because there is no alcohol in this situation. So respiration is still going to be the vector -1, -6, 6, 6. Photosynthesis is going to be, well, photosynthesis gives us a, I'm missing an O2 here. Photosynthesis is going to give us 6O2 actually, give us a glucose, 6 oxygen. It's going to use 6 CO2, and it's also going to use 6 water. It also uses some energy that chloroplasts get from the sun, but that's not part of the chemical equation. All right, so you can see that the span of these two vectors is very different than, if we wanted to, so actually, just so we can compare the two, why don't I, and I've messed up my window. I have been having a very hard time with OneNote because it doesn't, it is not smart. When I hit a button on my pen, it sort of freaks out on me. So let me fix it, reshare it. Okay. So we could add one last entry for alcohol, but it's going to be 0 for both of these. So if we take the span of these two, well, since the second one is actually just the negative of the first one, this is actually just the span of just the first one, -1, -6, 6, 6, 0, right? So we could compare these two spans and have a good handle on how the possible collection of moves, or how the collection of actual moves we can make, given these two sets of reactions, is very different, right? In this example, this span is just a line instead of a whole plane. So we get a very different kind of collection from these two reactions than we do from respiration and fermentation. Setting things up this way does have some assumptions, right? Because with span, we take all linear combinations of these vectors, and all linear combinations includes combinations that have negative coefficients and fractional coefficients, which may or may not make sense in some applications. Now, in this application, negative coefficients may make sense because if we look at this reaction, that taking the negative of this would just flip all these signs. That's just doing this reaction in reverse, which makes sense because after all, that's what photosynthesis is, if you ignore the energy input and output of everything. So in this context, negative coefficients could make sense. But what about fractional coefficients? Well, if these coefficients, if the units for these coefficients are actually individual molecules, it wouldn't make sense to have half of this reaction, because you couldn't use up half of a sugar molecule and produce half of a water molecule. That's not how chemistry works, right? You have to use up a whole molecule and produce a whole molecule. But if we changed the units and said that all of these entries, the units for these were moles instead of molecules, then we could have fractional exponents, because a mole is a lot of molecules, and so it makes sense to divide moles into fractions. So This just goes to show that when linear algebra meets applications, you have to be kind of careful about the assumptions that linear algebra makes, because those assumptions might not make sense in the application that you're working on.